also want to have out your unit circles too, because we are going to be starting I love this chapter. I'm not going to lie to you. If you guys could have been in the first class, they were getting all kinds of crazy. We were getting all kinds of crazy because this stuff just gets me all jazzed up. Okay? So, this stuff's, I love this stuff. Okay? So, new chapter, new semester, new everything. Okay? All right? So, what do we have to look forward to now? In this chapter, we will shift our emphasis towards more theory and proof. And math geeks like myself, we really love theory, and we really love proofs. Okay? Exploring where the properties of these special trig functions lead us, often with no immediate concern for the real-world relevance at all. Okay? We hope that in this process to give you an appreciation for the rich and intricate tapestry, this is such a great sentence, of the interlocking patterns that can be woven from the 6 basic trig functions. Patterns that will take on an even greater beauty later when you can view them through the lens of calculus. I'd love to take credit for that, but my English skills would probably have only gotten that. I mean, I like to say that I can speak good, but I can't write good. Okay? So, today it's all about pretty. Okay? You know, it's not just me being a pretty man standing up here in a nice looking sweater vest. Okay? It's all about taking ugly things and making them look pretty, putting a little shine on them. Okay? Shining them up, spit polishing them a little bit, getting a nice good shine on. Okay? So, whoop, whoop, whoop. Tap the brakes. Tap the brakes. Got to go over here. Now we're back. All right, so we have to remember these things. And there used to be a picture on this slide, but we took it off because it was eating up some space. But it was from Pee-wee's Big Adventure, and he like passes out, and then he comes to, and they're like, "Do you remember where you are?" And Pee-wee says, "I remember the Alamo." And they all go, "Hooray!" Because he was in Texas at the time. Okay? It's a really good scene. Okay? But so we got to remember these identities. Now, I wrote them out here in terms of sine and cosine. Okay? So cosine equals cosine. Sine equals sine. Duh. Okay? Those are does. Okay? Secant, 1 over cosine. Secant and cosine are reciprocals. Not inverses, reciprocals. Okay? There's a difference there. Tangent is sine over cosine. Cosecant is 1 over sine. Cotangent is cosine over sine. Okay? We learned all of those first semester. Okay? We also learned the hammer. Sine squared plus cosine squared equals 1. But what if I take the hammer here, because I can manipulate that one because there's an addition sign there, and what if I subtract sine squared from both sides? Well, then I would get cosine squared of theta equals 1 minus sine squared of theta, right? Okay. What if you don't like subtracting sine squared from both sides? What if you're subtracting cosine squared from both sides? Well, then you would get sine squared of theta equals 1 minus cosine squared of theta. Which, if you look on your unit circle sheet on number 7, the hammer is 7a, right? 7b is, I think it's the blue one, and 7c is the orange one. Okay? So it's just different ways of writing the same stuff. Okay? Because what this section is all about is one, we're going to simplify expressions. We're going to simplify trigonometric expressions. Okay? And that's a lot of fun. Okay? Then, on Friday, we're going to start proving trigonometric we're going to start solving trigonometric equations. And that's even more fun. And then next week, we're going to start proving trigonometric equations. And that is thebomb.com. Okay? That's where the fun stuff happens. Because you take this ugly looking thing and, yep, you prove it that one side equals the other. Okay? Today we're just going to take this ugly looking thing and we're going to make it nice and pretty. Just like, okay? All right? So, back to the hammer. Okay? So, sine squared plus cosine squared equals 1. We should have that memorized by now. What if I don't want to subtract? What if I want to divide? Okay? So let's say that we divide both sides by sine squared. Well, if I divide both sides by sine squared, I'm really dividing every term by sine squared. Okay? So if I divide every term by sine squared, my very first term, what does that become? That's just 1, right? Sine squared divided by sine squared, that's just 1. This next term, I can't really change anything with it, right? Okay, so that's going to be cosine squared of theta over sine squared of theta. Okay. Oops, probably should have done this. Done it this way. And then this one over here. Oops, I did purple already. I did red. And I did. No, didn't do blue. Right? Now, I asked you cosine squared over sine squared. That looks a lot like cotangent, right? Because cotangent is cosine over sine. So cotangent squared would be cosine squared over sine squared. So this side is really 1 plus cotangent squared of theta. 1 over sine squared of theta is what? Is what? Cosecant squared, right? Okay. So if these three right over here were number 7 on your unit circle, then this one is, I want to say it's number 11. Cosecant, 1 plus cotangent, that's number 11, right? 10? 10? Number 10. What I'd like you to do now is I would like you to follow that same process, and I'd like to see what you come up with if we divide the hammer by cosine squared. So if I'm dividing everything now by cosine squared, this first one becomes what? Sine squared over cosine squared is tangent squared. Cosine squared divided by cosine squared is 1. 1 over cosine squared is secant squared. Okay. And that is that one number 11? Yeah? Yep. That one's number 11. So we're going to utilize those relationships, and the relationships that we have basically now, 1 through 11, we've learned so far now on our unit circles. Okay? And we're going to take something like this that's kind of not pretty, and we're going to make it be pretty. Okay? So one thing that we can do is we could say, well, the secant of negative x, according to, let me go grab a fresh one for myself. According to number 4, the secant of negative x here would be the secant of x. Agree? And that is going to be multiplied by the cosine of negative x, according to number 1, is just the cosine of x. Now, you may be saying to yourself, Linz, what did we really do there? Well, what we did is we got rid of the negative angles. We brought it back into positive angles for us. Okay? But what we also did is we can say that secant here is 1 over cosine of x. And when I multiply that by cosine of x, I get cosine of x over cosine of x. Which is just 1. So secant of negative x times cosine of negative x simplifies to be just 1. Okay. Secant squared of x minus tangent squared of x. I could change secant squared of x to just be 1 over cosine squared of x. And tangent squared of x is sine squared of x over cosine squared of x, right? And I could go through that way. Or I could say that something along the lines of secant squared of x, according to number 11, is tangent squared of x plus 1. Tangent squared of x plus 1 minus tangent squared of x is what? Tangent squared plus 1 minus tangent squared. It's what? It's just 1. The two tangent squareds cancel each other out, and that just leaves me with 1. Or we could have said that tangent squared is secant squared minus 1. Right? Because we can manipulate number 11 and solve that for tangent squared. And then replace it with tangent squared. My point is that we are standing at Wausau West right now. If we want to go to Mosinee, there's a ton of different ways that we can get down to Mosinee. One of the ways might be going out to Marathon and then coming in the back roads. It might be longer to go that way, or there might be just jump on the highway and go right there. Either way, we're all getting to that destination. It doesn't matter what path we take to get to the destination, we got to the destination. Okay? So your neighbor might have gone about this one a different way, or the next two examples that you're going to do on your own. Your neighbor might go about it a totally different path than you do, and that's okay, as long as you both get to the same destination. Okay? There's no one right way. Okay? So let's try some. what I would like you to do now is I would like you, whoa, come on back to me. Simplify those two. Tangent of x is sine of x over cosine of x. Multiply that by cosine of x, and you're left with sine of x. Secant of x is 1 over cosine of x. Cotangent of x is cosine of x over sine of x. Multiply those two together, and you're left with 1 over the sine of x, which is cosecant of x. Agree? Okay. All right. Try a couple more. Try some more involved type ones. So if I were doing this particular problem and I see this, I would think, because I don't have any squared terms in there, I'm going to be thinking to myself, all right, let's distribute. Okay? So if I distribute that, then I get the sine of theta times the cosecant of theta minus sine squared of theta. Agree with me on that? Sine of theta cosecant of theta is sine of theta times 1 over the sine of theta. So that's really sine over sine, which is just 1. So we have simplified it down to 1 minus sine squared of theta, which is, according to 7b, cosine squared of theta. Okay. In number 6, because I have a squared term right there, that probably means that's one of the identities that I have on my unit circle, and it's actually 7c, isn't it? The sine squared one? 1 minus cosine squared is sine squared. And actually, cosecant is 1 over sine, right? So sine squared times 1 over sine is sine squared over sine, which is just the sine of x. Okay. Your turn again. What I'd like you to do is I'd like you to simplify those two. Cosecant is 1 over sine. Secant is 1 over cosine, which means we flip those to multiply. So then this becomes 1 over sine, or we flip the purple one, I should say, to multiply it. Cosine over 1. Multiply those two across, and we get cosine over sine, which is cotangent. Tangent squared plus 1 is what? Secant? Or secant squared, I should say, of u. Yes? Secant squared of u times cosine squared. So secant squared then is 1 over cosine squared. Cosine squared times 1 divided by cosine squared is just 1. Yes? Again, might have gone a different way. Okay? You might have switched tangent to sine squared over cosine squared. Okay? Then distributed in, and then you would have had, sine squared plus cosine squared, which is the hammer, which is 1. Okay? Totally. And we're just fine with you going whichever direction you want to. Okay? Just when you think it's that easy, I go and I make it harder. Okay? Factoring. We can still simplify by factoring. So this one, number 9 here, not the prettiest looking trigonometric expression ever. Okay? But I can factor out a sine. That leaves me, so remember, when I'm factoring out, I'm still going to have two terms. They're still going to be separated by a negative sign because I didn't factor out a negative at all. Okay? Sine of x divided by sine of x, well, that's just 1. Sine of x cosine squared of x is cosine squared of x. One minus cosine squared of x, this becomes sine squared of x. Sine of x times sine squared of x is sine cubed of x. So that big, this ugly looking thing is really just sine cubed. Okay. What I would like you to do now is the same, but now with factoring. I would like you to simplify numbers 10 and 11. Alrighty. So I would factor first out a cosine squared. That's going to leave me with 1. Well, that's going to leave me with plus 1. No, that's going to leave me with 1 plus tangent squared of theta. 1 plus tangent squared, what's that? Secant squared? And secant squared is 1 over cosine squared of theta. So we get cosine squared over cosine squared, which is just 1. down here, I would first factor out a sine of x. That leaves me with sine squared of x plus cosine squared of x. And this is just 1. So this is just sine of x. Okay. Yep. Yeah, buddy. Love it. Okay. So we have factoring too. And we'll have factoring when it comes to solving too. And all will be well with the world. Okay? So, for your second F-bomb of the day, okay, we've got fractions too. Okay? Now, way back, we say 6th grade there, but it probably was more like the 5th grade when you guys started adding and subtracting fractions. Okay? So back in the 5th grade, you had an elementary teacher that probably said, oh, adding and subtracting fractions is awesome. And hopefully they had a ton of energy when they did it, because they got you all jazzed up to add and subtract fractions. Okay? Does anybody remember what the process is to add and subtract fractions? What do we got to do first? We got to find a common denominator. We got to find a number that both of the denominators go into. Now, we could go with the smallest one, or we could go with any one, really. It doesn't matter. Okay? Right? So, I'm looking at 3 and I'm looking at 5. And I'm thinking to myself, what goes into, or what does 3 and 5 both go into? 15 or 30 or 45 or 60 or 120 or anything. Okay? But I'm going to pick 15. So we first got to find, or you learned back in 5th, 6th grade, somewhere around there, you first got to find a common denominator. Awesome. Okay? Then that teacher probably told you, hey, now that you found your common denominator, now you take this number and you see what multiplies by it to get your common denominator. And in this case, it's being multiplied by 5. So you take the top of that and you also multiply that one by 5. 1 times 5 is 5. And you adjust your fractions to fit your common denominator. And then they said, now you do the same over here. So that one's times 3. So this one has to be times 3. So that one's 6. Then what do you do? Add what? Add the tops. Yep. So 5 plus 6 is 11. What about the bottom? Do I add those too? No, that stays the common denominator. So that stayed 15. And then what did we have to do? Simplify, right? Now, I'm going to ask you this question, and I'm going to relate it to the next one too. So I've got 11 over 5, right? Or excuse me, 11 over 15, right? Can I simplify this fraction by going like this? Can I do that? They both have a 1. Why can't I do that? Doesn't make any sense, right? Okay? Remember that going forward. Okay? Because that's algebraic. That's the most common mistake with fractions. People, oh, well, there's a 6 there and a 4 down there. I can reduce those two. Not if something else is on there. Okay? So that doesn't work. Okay? All right. Fast forward a couple years from 6th grade. I don't know when you took Algebra 1, but when you got into Algebra 1, now they said, oh, we got algebraic fractions for you. And you're like, why can't I just use my calculator? Okay. Well, you can't because of algebraic fractions. Okay. But then your algebra teacher probably told you, don't worry. It's just like when you were in 4th or 5th grade and how you added and subtracted fractions back then. First thing you do is you find your common denominator. Well, here, in this case, the common denominator is x times x plus 1. Right? And then they said after you find your common denominator, now you got to adjust your fractions. So this first one has to be multiplied by x. 1 times x is x. This second one, oops, I went purple. The second one has to be multiplied by x plus 1. So you get that. Then you got to add your tops. And that's all over your common denominator. And then you got to simplify. Well, this top really is x plus 2x plus 2, which is really 3x plus 2. Right? Now, I ask you again, just like the ones from the numeric problem, right? Can I do this? Ooh, that's not very good colors. Let's go here. Can I do that? Can I cross off those x's? But there's an x on top and there's an x on the bottom. Right? I can't do that. That's not good maths. And we're all about doing good maths. So then that becomes your answer. Okay. Now, fast forward a couple more years. Now, you're sitting in 221. It's almost the end of the first day of the second semester, and some pretty-looking teacher in a sweater vest tells you, now we're going to do trigonometric fractions. And he says that it's done the exact same way as your Algebra 1 teacher told you, which is done the exact same way that your elementary teacher told you on how to add basic fractions. What's the first thing we got to do? Find a common denominator. So let's find a common denominator for these two. What's my common denominator for those two? I need a 1 plus cosine, right? And I need a sine. So that's probably going to be sine of theta and 1 plus cosine of theta. What's the next thing we do? We adjust the numerators now. So to go from here down to there, I had to multiply by sine. So I have to multiply the top by another sine. So that one becomes sine squared. To go to this one, I had to multiply by 1 plus cosine, so the top has to be multiplied by 1 plus cosine. Now what? Not yet. I got to do something first before it becomes the hammer. I got to add them together first. Yep, I got to add them together first. So I got to go sine squared of theta plus cosine of theta times 1 plus cosine of theta all over sine of theta 1 plus cosine of theta. Now you're saying distribute that cosine? Now I like that, yep. So now I'm going to distribute this cosine in here. Okay. Now we're on to that simplifying stage that we had, that your teacher way back in elementary school told you to do. So then this becomes sine squared of theta plus cosine of theta. Actually, here, let's do it this way. Here, I'll go like this. Plus cosine of theta plus cosine squared of theta all over sine of theta 1 plus cosine of theta. And so then what are you saying, Uncle? That's 1. So the two black ones there, that becomes 1, right? Okay, love it. So then this is 1 plus cosine of theta all over sine of theta times 1 plus cosine of theta. Love it. Now what? The 1 plus cosines of theta, because if I'm thinking about this whole top as in a set of parentheses, so then that cancels that, which leaves me with 1 over sine of theta, which is what? Cosecant of theta. So this whole nasty looking fraction, if I can scroll back up to it, I can't fit it. Look at that. Okay. So that whole ugly looking fraction where you got to add two fractions together really just boils down to, after you simplify it, all it is cosecant. Okay? We're taking ugly looking things and we're making them look like lens. Pretty. Okay? Okay? That's all I got for you today. Thanks for playing along.